General Motors made a specific engineering decision that raises an important question. Why didn't they integrate a transmission electro-hydraulic control module, or TEHCM, into their 8L90 and 10L80 transmissions? These are GM's 8L90 and 10L80 automatic transmissions, complex mechanical systems with hundreds of precisely engineered components. Unlike many modern transmissions, GM chose not to integrate electronic control directly into the transmission housing. This question requires us to think like electromechanical engineers, analyzing multiple technical factors that influence design decisions in complex automotive systems. Our engineering analysis will examine four critical factors: thermal management challenges, serviceability implications, design complexity considerations, and risk assessment. Each factor played a role in GM's decision-making process. By examining these factors systematically, we'll understand the engineering rationale behind GM's choice and gain insights into how complex automotive systems are designed and optimized. Traditional automatic transmissions and modern electro-hydraulic systems represent two fundamentally different approaches to controlling gear changes. Understanding these differences helps explain why transmission manufacturers make specific design choices. Traditional automatic transmissions rely on purely hydraulic control systems. These systems use mechanical valves that respond to hydraulic pressures to determine when and how to shift gears. This diagram shows a traditional hydromatic transmission with its complex network of mechanical components, hydraulic circuits, and valve bodies that work together to control gear changes through purely hydraulic means. In hydraulic systems, pressurized transmission fluid flows through carefully designed circuits. The pressure and flow of this fluid directly controls valve positions and ultimately determines shift points. Now let's examine how electro-hydraulic systems revolutionize this approach by introducing electronic control over hydraulic functions. Electro-hydraulic control systems, like those found in TEHCMs, combine electronic intelligence with hydraulic power. Instead of relying solely on mechanical valves, these systems use electronically controlled solenoids. This electronic control unit represents the brain of an electro-hydraulic system. It processes sensor data and sends precise commands to solenoids that regulate hydraulic pressure with much greater accuracy than mechanical valves alone. Electronic control allows for real-time adjustments based on driving conditions. The system can instantly modify shift timing, pressure levels, and even learn from driver behavior to optimize performance. The key difference lies in precision and adaptability. While hydraulic systems provide reliable mechanical control, electro-hydraulic systems offer the intelligence to optimize every shift. Electro-hydraulic control systems provide several key advantages over traditional hydraulic systems. These benefits explain why modern transmissions increasingly adopt electronic control methods. This evolution from mechanical hydraulic control to intelligent electro-hydraulic systems represents a fundamental shift in transmission technology, enabling the precise, responsive control that modern vehicles demand. When considering TEHCM integration, one of the primary challenges is the significant increase in design complexity that comes with combining multiple components into a single module. A TEHCM combines sensors, solenoids, control electronics, and often the transmission control module itself into one integrated unit. This creates a web of interdependent components. This valve body shows the physical complexity involved. 7 solenoids, intricate hydraulic channels, and electronic connections must all work together seamlessly. However, this integration creates a critical vulnerability: concentrated failure points. When components are integrated into a single module, the failure of any one component can compromise the entire transmission control system. This circuit board analysis shows various failure modes: corrosion, burnt components, and electrical damage. In a TEHCM, any of these failures would require replacing the entire expensive module. This complexity directly translates into significant cost implications across multiple areas. The relationship between complexity and cost is not linear. It grows exponentially. As we integrate more components, the design challenges multiply, manufacturing precision requirements increase, and potential repair costs skyrocket. Design costs increase due to complex integration challenges. Manufacturing requires higher precision and specialized assembly processes. Most critically, Repair costs can be dramatically higher since individual component replacement becomes impossible. The fundamental trade-off becomes clear. While TEHCM integration can streamline assembly and potentially improve control precision, it concentrates failure points and significantly increases both manufacturing and repair costs. For GM, this risk-cost analysis likely influenced their decision to avoid TEHCM integration in the 8L90 and 10L80 transmissions. Understanding these complexity and cost considerations provides crucial insight into transmission design decisions. Thermal management is one of the most critical challenges when integrating electronic components into automotive transmissions. Heat is the enemy of electronic reliability. Modern transmissions generate tremendous amounts of heat during operation. Internal friction from gears, clutches, and hydraulic pumps creates temperatures that can exceed 200 degrees Fahrenheit under normal conditions. Electronic components like sensors and control modules are extremely sensitive to heat. High temperatures cause semiconductor materials to degrade, solder joints to weaken, and circuit boards to warp or crack. The GM 8L90 and 10L80 transmissions are particularly known for running hot, especially under heavy load conditions like towing or performance driving. This creates a hostile environment for any electronic components placed inside. Research shows that for every 10 degrees Celsius increase in temperature, the failure rate of electronic components approximately doubles. This exponential relationship makes thermal management absolutely critical for reliability. This thermal challenge explains why placing a TEHCM directly inside a transmission presents significant engineering obstacles. The combination of high heat and vibration creates an extremely harsh environment for sensitive electronic components. Electronic components within a TEHCM are highly sensitive to temperature variations. Understanding how overheating causes specific failure modes is crucial for transmission reliability. Temperature sensors are among the first components to fail when exposed to excessive heat. These sensors provide critical feedback about transmission fluid temperature and component operating conditions. Control solenoids are equally vulnerable to heat damage. These electromagnetic devices control hydraulic pressure and flow within the transmission valve body. Here we can see the physical valve body where solenoids are mounted. The close proximity of electronic components to hot transmission fluid creates thermal stress. As temperatures exceed safe operating limits, electronic components begin to degrade. Solder joints weaken, insulation breaks down, and semiconductor materials lose their electrical properties. These component failures manifest as specific transmission problems. Sensor malfunctions lead to incorrect temperature readings and poor shift timing. Solenoid failures cause erratic hydraulic pressure control. Maintaining optimal operating temperatures is absolutely critical for TEHCM longevity. Effective thermal management systems must be designed to protect these sensitive electronic components from heat-induced failures. From General Motors' business perspective, repair costs represent a critical factor in both customer satisfaction and long-term profitability. The company must carefully balance engineering decisions with their potential impact on warranty expenses and consumer repair bills. Given the existing reliability concerns with the 8L90 and 10L80 transmissions, GM faced a strategic decision. Adding a TEHCM system could potentially increase repair complexity and costs, which would directly impact both warranty expenses and customer out-of-pocket costs. The financial implications extend beyond individual repair costs. GM must consider warranty expenses, which directly impact their bottom line. A more complex system that requires complete module replacement could significantly increase warranty claim costs across their vehicle fleet. Customer satisfaction and brand reputation are directly tied to repair costs and reliability. High repair bills can damage customer loyalty and create negative publicity. GM recognized that introducing a system that could increase repair complexity might harm their reputation, especially given existing transmission issues. This strategic decision reflects GM's understanding that engineering choices have far-reaching business implications. By avoiding TEHCM integration, GM prioritized keeping repair costs reasonable for consumers while protecting their warranty expenses and brand reputation in a competitive automotive market. When developing complex automotive systems like transmissions, engineers must carefully balance innovation with practical constraints. Integrating HCM represents a significant technological leap that comes with substantial development challenges. The difference in complexity between traditional transmission control and TEHCM integration is substantial. Traditional designs use separate, proven components that have been refined over decades. In contrast, TEHCM integration requires coordinating multiple advanced systems into a single unit. This integration introduces new challenges in thermal management, vibration control, and electronic reliability. Development timelines reveal the challenge. Traditional transmission designs follow well-established development paths, typically requiring 36 months from concept to production. TEHCM integration extends this timeline significantly, often requiring 48 months or more. The additional complexity introduces multiple points where unforeseen problems can emerge, potentially causing further delays. Looking at the complexity of modern transmission components, we can understand GM's strategic thinking. This valve body shows the intricate solenoid arrangements that must be precisely controlled. Rather than adding TEHCM complexity to an already challenging system, GM chose to focus their engineering resources on perfecting the core transmission mechanics and control software. This approach minimized development risk and accelerated their time to market. This comprehensive transmission diagram illustrates why integration decisions are so critical. Each component must work in harmony, and adding TEHCM integration would require extensive redesign and testing of the entire system. By choosing a traditional design approach, GM was able to deliver reliable transmissions to market faster while maintaining lower development risk. This strategic decision prioritized proven technology over cutting-edge integration. The existing design architecture of GM's 8L90 and 10L80 transmissions presents significant constraints for integrating a TEHCM or mechatronic unit. These transmissions are fundamentally based on a gearset concept similar to the ZF 8HP transmission family. This architectural foundation was chosen for its proven performance and efficiency. The challenge with this existing architecture is that it was designed around traditional hydraulic control systems, not integrated electronic control modules. A TEHCM requires specific mounting locations, electrical connections, and thermal management considerations that weren't part of the original ZF-based design. Integrating a TEHCM would require major redesign of the valve body, case modifications, new wiring harnesses, and potentially restructuring the entire hydraulic control system. Given these architectural constraints, GM likely determined that the cost and complexity of a complete redesign outweighed the potential benefits of TEHCM integration, choosing instead to work within the existing proven architecture. When faced with transmission challenges, General Motors had two paths: completely redesign with new technology like TEHCM, or focus on refining their existing designs. GM chose the refinement approach. This strategic decision represents a fundamental choice between incremental improvement and radical innovation. Let's explore why refinement often makes more business sense than complete overhaul. General Motors itself demonstrates the power of incremental refinement. Look at how their logo evolved over more than a century, not through radical changes, but through careful, thoughtful improvements. This incremental approach is fundamental to automotive innovation. The entire automotive industry has evolved through continuous refinement rather than revolutionary leaps. Consider automotive evolution over the past century. Each decade brought improvements, but the fundamental concept remained consistent: gradual enhancement rather than complete reinvention. For GM's 8L90 and 10L80 transmissions, this refinement approach meant improving existing electronic control units, updating software calibrations, and enhancing mechanical components, all while maintaining the proven foundation. This refinement approach offered GM significant advantages: reduced development time, lower costs, minimized risk of introducing new failure modes, and the ability to leverage existing manufacturing processes and supplier relationships. By choosing refinement over radical redesign, GM could address known issues systematically while avoiding the complexity and uncertainty that would come with implementing an entirely new HCM system. This strategic decision reflects sound engineering judgment in balancing innovation with practical business considerations. Transmissions operate in an extremely harsh vibrational environment. NVH, which stands for noise, vibration, and harshness, represents critical engineering challenges that directly impact the reliability of electronic components. Automatic transmissions generate significant vibration from multiple sources: gear meshing, hydraulic pump operation, torque converter lockup, and engine harmonics. These vibrations create a challenging environment for sensitive electronic components. In a THCM design, electronic components would be mounted directly onto the valve body inside the transmission. This location subjects them to the full intensity of transmission vibrations, creating reliability challenges for sensitive electronic circuits. Vibration particularly affects solder joints and electrical connections. As shown in this image, repeated stress cycles cause solder joints to crack and fail. These failures often manifest as intermittent problems that are extremely difficult to diagnose and repair. Electrical connectors are equally vulnerable to vibration damage. Constant movement causes pin fretting, changes in contact resistance, and intermittent signal loss. These connector-related failures can cause erratic transmission behavior that appears and disappears unpredictably. The intermittent nature of vibration-induced failures makes them extremely challenging to diagnose. Problems may appear only under specific operating conditions, disappear during testing, and fail to trigger consistent diagnostic trouble codes. This creates frustrating repair scenarios for both technicians and vehicle owners. These vibration and NVH considerations represent a significant engineering challenge for THCM integration. The harsh vibrational environment inside transmissions can compromise electronic reliability, leading to expensive and difficult-to-diagnose failures that impact both customer satisfaction and warranty costs. Automotive transmissions operate in extremely harsh environments with constant vibration from the engine, road conditions, and internal mechanical components. For electronic systems like THCMs, these vibrations pose serious engineering challenges. Vibrations can cause catastrophic failures in electronic components. Solder joints crack, connectors loosen, and circuit boards develop stress fractures. These failures often appear as intermittent problems that are difficult to diagnose. Engineers use sophisticated vibration damping systems to protect sensitive electronics. These systems typically consist of multiple layers: a vibrating surface, a damping material that absorbs energy, and a constraining layer that controls the damping behavior. Real THCM units like this valve body assembly contain numerous sensitive components. Each solenoid, sensor, and electronic control module must be individually protected from vibration while maintaining precise hydraulic control. Robust mounting systems are essential for THCM reliability. Engineers must design specialized brackets, isolators, and damping materials that can withstand years of constant vibration while maintaining precise positioning of electronic components. However, these vibration mitigation strategies significantly increase both cost and complexity. Advanced damping materials are expensive, specialized mounting systems require precise manufacturing, and the additional components add weight and assembly time to the transmission. Effective vibration management is absolutely crucial for ensuring the long-term reliability of electronic components in harsh automotive environments. Without proper protection, even the most sophisticated TEHCM will fail prematurely, leading to costly repairs and customer dissatisfaction. While General Motors' specific internal research and failure analysis data remains proprietary and confidential, we can make educated inferences about their decision-making process by examining the well-documented problems with the 8L90 and 10L80 transmissions. By analyzing the transmission's internal components and documented failure modes, engineers can understand the challenges GM faced when considering TEHCM integration. This cutaway view shows the complex mechanical and hydraulic systems that would need to work alongside electronic controls. The 8L90 and 10L80 transmissions have several well-documented problems that provide insight into GM's engineering challenges. These include torque converter shudder, harsh or delayed shifting, valve body cross leaks, and input shaft fragility issues. This valve body with its complex solenoid array illustrates the challenge. When mechanical components like valve bodies already have reliability issues, adding integrated electronics through a THCM would compound the risk. If the underlying hydraulic system fails, the entire electronic module becomes compromised. The engineering insight here is clear. GM's internal failure analysis likely revealed that the existing mechanical and hydraulic problems needed to be resolved before considering complex electronic integration. A TEHCM would not solve the underlying issues and could potentially amplify existing failure modes, making repairs more complex and expensive. The GM 8L90 and 10L80 transmissions are frequently reported to have harsh or delayed shifting problems. These issues affect the driving experience and raise questions about whether a TEHCM could have provided better control. Let's visualize the difference between normal and problematic shifting. Normal shifting should be smooth and seamless, while the 8L90 and 10L80 often exhibit harsh jolts or delays between gear changes. The shifting problems stem from several potential causes. Solenoids control hydraulic pressure to engage and disengage clutches, but they can fail or stick. Valve body internal leaks affect pressure regulation, and software calibration determines shift timing and firmness. The valve body contains intricate hydraulic circuits with multiple pressure points and solenoid connections. While a TEHCM could theoretically provide more precise electronic control over these systems, it introduces additional complexity without addressing the root mechanical problems. A TEHCM integrates multiple electronic components into a single complex unit. While this can improve control precision, it also means that if any component fails, the entire expensive unit must be replaced. For transmissions already experiencing mechanical problems, this added complexity may not be the optimal solution. In conclusion, while a THCM could theoretically provide more precise shift control, the harsh and delayed shifting problems in GM's 8L90 and 10L80 transmissions appear to stem from fundamental mechanical issues, solenoid failures, and calibration problems that a TCM integration might not effectively address. The automotive industry is experiencing a fundamental transformation. The rapid shift toward electric vehicles is reshaping how manufacturers think about powertrains and transmission technology. Traditional internal combustion engines require complex multi-speed transmissions to efficiently deliver power across different driving conditions. Electric motors, however, operate very differently. Electric motors provide instant torque and maintain high efficiency across a wide range of speeds. This eliminates the need for complex multi-speed transmissions that traditional vehicles require. General Motors recognized this industry shift early and began investing heavily in electric vehicle technology. This strategic pivot has significant implications for their transmission development priorities. The electric vehicle charging infrastructure is experiencing explosive growth, with the market projected to reach nearly $183 billion by 2030. This rapid expansion supports the viability of the EV transition. This fundamental shift in the automotive landscape influenced GM's strategic decisions about transmission development. Why invest heavily in complex transmission technologies when the future lies in electric drivetrains that don't need them? The electric vehicle transition represents more than just a technology shift. It's a complete reimagining of automotive powertrains. For GM, this meant prioritizing EV development over incremental improvements to traditional transmission technology like THCM integration. Modern transmission control has evolved from purely mechanical systems to sophisticated software-driven solutions. General Motors has strategically focused on refining transmission control algorithms rather than investing in more complex hardware like THCMs. The choice between software-based and hardware-based solutions represents a fundamental engineering decision. Software control offers flexibility and cost-effectiveness, while hardware integration brings complexity and higher development costs. GM's transmission control algorithms are the brain of the system, making thousands of decisions per second to optimize shifting performance, fuel efficiency, and driver comfort. Software updates allow GM to continuously improve transmission performance without hardware modifications. These updates can address shifting issues, improve fuel economy, and enhance overall driving experience. This software-focused approach allows GM to address transmission issues quickly and cost-effectively, providing continuous improvements to existing vehicles while avoiding the complexity and expense of hardware redesigns. General Motors has taken a proactive approach to addressing transmission issues through continuous improvement efforts and technical service bulletins, or TSBs. Technical service bulletins are official communications from manufacturers to dealerships and technicians. They provide updated repair procedures, software calibrations, and hardware modifications to address known issues. GM has released numerous updates for their 8L90 and 10L80 transmissions. These bulletins address everything from software recalibrations to hardware component replacements. These improvements fall into two main categories: software calibrations that optimize shift patterns and timing, and hardware modifications that address mechanical weaknesses in components. This commitment to continuous improvement is evident in the detailed technical documentation and comprehensive understanding of transmission components that GM maintains. This approach demonstrates that rather than completely redesigning with new technologies like TEHCM units, GM chose to refine and perfect their existing transmission architecture through iterative improvements. This continuous improvement strategy shows GM's dedication to maximizing the performance and reliability of their existing transmission designs, rather than starting over with completely new architectures.